Today we're taking a look at graphing linear inequalities in the coordinate plane. Now you'll remember when we graphed equations in the coordinate plane, it was the set of all those points that satisfied that equation. Well, today when we graph an inequality, we're actually looking for a feasible region or a set of many points that satisfy the inequality. There are four cases that we're going to consider. The first case is when y is greater than mx plus b. Now you'll notice that we have a dotted line here because y cannot be equal to mx plus b. It's only the solutions that are greater than. So this is going to divide our coordinate plane up into two feasible regions here, or two half planes, and the region that we want are all the y's that are greater than that line. The next possible case is when we have y's greater than or equal to, and you'll notice now that our line is a solid line, and that again we are shading above where that line splits our y-axis because we want all the y's that are greater than or equal to that line. The next case is where y is less than mx plus b, and again here you're going to see a dotted line, and that dotted line indicates that it cannot be equal to the points on that line, but it in fact is the region that appears below that dotted line because it's all the y's less than. The next possible case here is when y is less than or equal to mx plus b, and again you'll notice that we have a solid line and our shading appears below that solid line, and it also includes that solid line. Alright, let's take a look at a few examples here and see how we would graph these in our coordinate plane. Our first example here, we have y is greater than or equal to negative 3. Well, you'll recall that the equation y equals negative 3 is a horizontal line passing through the y-axis at negative 3. And because it can be equal to negative 3, we are going to graph a solid line passing through our y-axis here at negative 3. So here's our line y equals negative 3. Now we want all the y's that are greater than it, so we are going to shade this half plane that appears above because this indicates all of our y's that are greater than or equal to our line. So this is known as our feasible region, or our half plane in which our solutions exist. Whew, that was a tongue twister. All right, let's take a look at the next one. We got x is greater than 4. So you'll remember that the line x equals 4 is a vertical line that passes through the x-axis at 4. Now you'll also note that this is x greater than 4, but not equal to 4. So this indicates that we need a dotted line, dotted vertical line going through the x-axis here at 4. And we want all the y's that are, we want all the x's that are greater than 4. So that means we're going to shade to the right, indicating that this is my solution set here. Any coordinate here, actually, to the right in this shaded area would be a solution to this inequality. All right, now moving on to our next example, we are going to graph the inequality. We want all the y's that are greater than 2x minus 1. So let's start off by acknowledging what our slope and our y-intercept are. So our y-intercept here is at negative 1, and the slope of this line is 2. So we'll rise 2 and run 1 and repeat to get some points that our line will be constructed of. Now, take special note of the inequality. We want all the y's that are greater than, but not equal to. So this indicates that this needs to be a dotted line. So I will make some dots through the points that I've already made, and we'll continue those dots off in this pattern here. So here is the dotted line of 2x minus 1. Now we want all the y's that are greater than. So again, keep in mind, here's our y-axis, and here's the region where all of our y's are greater than that line. So we know to shade above our line here. So this region here, or this half plane, is the solution to this inequality. So we want to shade everything above this y-axis. Or sorry, we shade everything above our line 2x minus 1. All right, one more example here we are going to take a look at. We have a ferry boat that carries cars and buses across Lake Michigan. The boat has space for 12 cars. A bus takes up the space of 3 cars. We want to draw a graph that shows all the possible combinations of cars and buses that can be taken in one crossing. So it's important for us to define our variables. Let's let x equal the number of cars, and let's let y equal the number of buses. All right, once we've defined that, now we want to write an inequality. We know that x plus 3y has to be less than or equal to 12. So here's what we're saying here. X is the number of cars. They all count for one space. Buses, or y I should say, is the number of buses, and they all count for 3 spaces. When we combine buses and cars, they have to add up to be less than or equal to 12 spaces in order for the boat to make the crossing. So here is our linear inequality written in standard form. We're just going to manipulate this to get slope-intercept form. So we'll subtract our x over and divide by 3. That gives us 3y is less than or equal to negative x plus 12 divided by 3. And so y is less than or equal to negative 1/3 x plus 4. Now we can go ahead and graph this line in slope-intercept form. So remember y is here. Our y-axis will be 4, or sorry, our y-intercept will be 4. Our slope is negative 1 and 3. Come down 1 and run 3. And we'll keep repeating that, down 1 and run 3. Now also keep in mind your y's were your number of buses and your x were your number of cars. So we should go ahead and label, this is 1, 2, 3, 4, all the way out here to 12. And then we have number of buses, 1, 2, 3, 4. All right, so our points here, I'm just going to highlight them in yellow, would be our line. Now we can construct a line, a solid line through this because we have all the y's that are less than or equal to. So I'm going to construct this solid line, and you might think that this would be a continuous function. However, remember this is a discrete function, so all the solutions are actually only the points where we have whole number coordinates. So in other words, we could take 1 car and 3 buses, or 1 car and 2 buses, 1 car and 1 bus, or simply 1 car. Now remember, these are the lattice points. Anytime where you have a coordinate that is an integer, both the x and the y are integers, these are known as lattice points. So our lattice points are actually all of our solutions to this linear inequality. And we're graphing it here on the coordinate plane, and you can see all of those lattice points and see all the possible solutions. So you could have 11 cars and 0 buses, 10 cars and 0 buses, or 9 cars and 1 bus. So this point here would indicate 9 over and 1 up. That would be 9 cars and 1 bus. So all of these lattice points are solutions for this linear inequality.